Welcome everyone. Thanks for joining my talk today. Talk will be about compute shaders. I'm Lou, I'm a developer technology engineer at AMD. And my job is basically to help with a lot of different, to work with a lot of different game developers and make sure that their game first that they run it all on AMD hardware, and then also that they run as fast as possible on AMD hardware. And I'm specialized on GPUs, so I'm basically mostly interested in what's happening on the GPU, what work gets submitted on the GPU, and to make sure that this is as fast as possible. So this talk is mostly about compute shaders. And the beginning will be very like an introduction. So if you're already kind of familiar with graphics programming, a lot of it will be known to you. But I still would cover it because it's very important that you understand the concept of it and also what it implies for the hardware. And then the second part of the talk is a bit more low level. I will talk about memory and caches and also about how shaders get executed on the GPU in general and what to know in order to write efficient code. And since I'm from AMD, I will focus on the RDNA 2 architecture, but the main concepts about how shaders get executed on GPUs, they are not specific to RDNA 2. There are some twerks that I will highlight that are mostly specific to RDNA 2, but most of the knowledge I will talk about today is transferable to other GPU architectures. Okay, but let's start with the more basic stuff. So I'm not sure if you watched my talk last year at the GIC, but I was giving a talk with the focus on the graphics pipeline. The talk itself was called All the Pipelines because I not only talked about the graphics pipeline, but also about the compute pipeline. But I just mentioned it very briefly, and the reason was that the graphics pipeline is way more complicated in comparison to the compute pipeline. And if you look at the compute pipeline from a logical point of view, you see it just as one stage, which is the compute shader stage. So it basically just exists of one stage of the shader itself. While if you look at the graphics pipeline has a lot of different stages, a lot of fixed function hardware. So it's way more rigid. And the compute pipeline is super flexible. So basically it's really up to you as a programmer what you want to do with your compute shader. Now, if you look at the hardware side, the compute pipeline on the hardware side is also way more simple compared to the graphics pipeline. So these are all the units you have on the hardware. And you see if you invoke a compute shader, not all the units are used because some of them are really installed to perform the fixed functions of the graphics pipeline, which we don't use if we use a compute shader. But of course, we still need the command processor because the command processor is a unit on the GPU that's getting all the commands from the CPU and basically decides what the GPU needs to do next. So if we submit a dispatch to invoke a compute shader, the command processor gets this command, and then it will basically tell the SPI, the shader processor input, what to do. And the shader processor input is the scheduler, so it's responsible for distributing the workload to all the available dual compute units. So that's still needed for a compute shader. But all the other things like the geometry engine, the shader export is not needed for a compute shader. So the dual compute unit, this is the unit where all the computation is happening. And for compute shaders, what's important is that all the inputs and outputs are provided via resources. So textures and buffers. Also the output is provided by textures and buffers. So you have writable resources. While if you use the graphics pipeline, so if you, for example, write the pixel shader, you usually have render targets, and then the outputs gets exported via the shader export, and then ends up in the color and depth backend. So that's a big difference, and I will talk about this a bit in the end of this talk. So, but first, how to dispatch a compute shader from the programmer's perspective. And so this is a very simple example. So you have a compute shader. So in this example, the compute shader is just doing sharpening, but really it doesn't matter what the compute shader is doing. It needs some sort of input, so we need some sort of input data. In this example, it's a simple input, one texture, read only. Then if you want, we can also provide some constants, maybe per frame data, or whatever, and then we need some sort of output. So in this case, it's a writable texture, and since it's a sharpener, the output will contain the more sharpened texture. So first, before you can submit the compute shader, you need to make sure that your resources are in the right state. So our input resource needs to be in the shader resource view, so non-pixel shader resource state, and the output shader needs to be in the unordered access state, so that means that it's writable. One hint here, please try to avoid to transition to the common state, because this can have an impact on performance. And this is not specific to compute shaders, but I still think it's worth mentioning it. If you try to avoid the transition to a common state. If you're already in common state, then just stay in common state. But if you're not in the common state, it's better to transition to, for example, the non-pixel shader resource compared to common state. And then, if needed, then we also need to update our constants. Obviously, so for example, it could be the amount of sharpening you want to apply in this example, or whatever else the constant you provide. Then we need to bind the resources, so basically just letting the GPU know which resources we want to access and how we refer to them in the shader. And also we have to bind our compute pipeline, so basically bind our compute shader, and then we dispatch. So now how do we dispatch the shader, and like what do we need to know about this? So if you think about the graphics pipeline, so for example, if you have a vertex shader, and one vertex shader invocation operates on a single vertex. A vertex, basically, if you have your geometry, and your geometry consists of a bunch of vertices which are connected via triangles, and that's basically the definition, okay, that's the vertex. Then if you have a pixel shader, one pixel shader invocation works on a single pixel. So if you have your geometry, then the rasterizer is running for it, and it basically determines what pixels are covered by your geometry. Now for a compute shader, this single work item is called a thread. And what the thread is really up to you. So it's kind of like an abstract thing. But it's up to you as a programmer to define what the thread is actually doing and what output it generates. To look at an example, so you can do full screen passes using both the graphics pipeline or the compute pipeline. If you use the graphics pipeline for that, you usually have a like full screen triangle. So one triangle which is large enough that it covers the full screen. So this means that you have 3 vertices, 3 vertex shader invocations, and then as many pixel shaders as large your output target is. So in this example would be 1080p. For compute shaders, we basically have to explicitly tell that the number of threads we want to invoke. And this can be done in various ways. And so because you have like a hierarchy of work items when you dispatch a compute shader. So first you have the size of the dispatch itself, and then you have X, Y, Z dimensions. And this is basically defining how many thread groups you invoke. So in this example, you have a dispatch size of 432. So in total, you have 24 thread groups. And then a thread group is, well, it's a group of threads. And how many threads, it's also up to you. And you define it in your compute shader. So in this example, you have 8 times 2 times 4 threads in one thread group. So in total, 64 threads. So this means the total number of threads you invoke with this dispatch call is 24 times 64. And then if you look at a single thread, you have like different types of indices. For example, you have the index of the thread within the thread group, you have the index of the thread group itself, and you also have the index of the thread within the whole dispatch. So now if you have this in mind, then you can like deploy different approaches how you basically call your dispatch. So back again, the same example. We have like a full screen pass, the sharpener. We want 1080p output texels. So now we can write our computer in a way that each thread produces 1 output texel. That means we need in total 1080p threads, right? Now we can choose a thread group size of 8 by 8. So in total, we need 240 times 135 thread groups. Now we can change our approach. We can write our compute shader in a way that each thread produces actually 4 output texels. That means in total, we need less threads. If we still set our thread group size to 8 by 8, then we have less thread groups. Now we can also change the thread group size itself. We can say, oh, we don't want 8 by 8, but we want the thread groups of 8 by 4. But we still want, in total, the same amount of texels to be computed, so we need more thread groups. So you can play around with it. And it's not random how you choose these numbers. They have an influence on, potentially on performance, because they basically determine how your workload gets distributed to the GPU. Now, if you look at the GPU, so the GPU is designed to execute parallel workloads, right? That's why we have a bunch of dual compute units. So for the RX 6900 XT, for example, we have 40 dual compute units. And each dual compute unit has 4 32-wide SIMDs. So now, it's important to know that each thread group gets scheduled to an available dual compute unit. And then the threads within the thread group, they get schedules in WAVEFRONT. And on RDNA 2, the WAVEFRONT can have either a size of 32 or 64. So that means if we have a thread group of 64 threads, we know all these 64 threads end up on the same dual compute unit. But if you're running in WAVEFRONT 32 mode, which is kind of like the native way, then it can be that the first half, like the first 32 threads, end up in one SIMD, and the other 32 threads can up in the other SIMD. So we can't control this. This is up to the scheduler. And then we have all the 32 threads on the SIMD, and they get executed. And in case if you run WAVEFRONT 64, we basically schedule every instruction twice, and they get executed in lockstep. So, and this is really important to know, because this has consequences in how threads can communicate with each other, and when they're loading data from memory, how they end up in cache. And this is the next chapter. It's basically talking about memory and how threads can communicate with each other. So this is a diagram of RDNA 2, and this specific one is the RX 6900 XT, because if you count all the dual compute units, you will realize these are 40. But what I want to point out here are the different levels of memory you have in cache. So, I mean, of course, you have the global memory, which is the VRAM. And then you have different levels of cache, because like accessing data from the VRAM is quite slow. So that usually when you load the data, it gets also loaded into the cache, so that you have, if you have like subsequent reads, that it's faster. And the highest level is the infinity cache, which you see here, like these big blocks. And the infinity cache is quite large, and it's global. And global means that it's visible from all dual compute units. So every thread, doesn't matter on which dual compute unit it's running, is seeing what's happening in the infinity cache. And the same is true for the L2 cache. So the L2 cache is also global, but it's much, much smaller than the infinity cache. But it's also closer to the dual compute unit. So reading from the L2 cache is faster than the infinity cache. Then if we go one level further down, we end up in the L1 cache. And the L1 cache is not global anymore. So we have one L1 cache per 5 dual compute units, which means if we have a thread in this group of dual compute units, they see what's happening in this L1 cache. But a thread in this group does not see what's happening in this L1 cache. It's only seeing what is happening in its own L1 cache. So it's not global anymore. And then there's even one level further down, which is the L0 cache, and the L0 cache is unique per compute unit, not per dual compute unit. And in the next slide, you will see what I mean with that. And then we also have group shared memory. It's like a special type of memory which sits on the dual compute unit, and it's explicitly accessible to you as a programmer when you write compute shaders. And I will talk about it a bit, what it is and what you can do with it in a later slide. But let's look at the compute unit. And well, it says compute unit because it only highlights half of a dual compute unit. So if you look at the compute unit, you see like two SIMDs accessing one L0 cache. And then there's a second L0 cache, actually. It's just here. And this L0 cache is visible to the other two SIMDs. While when you look at the local data share, which is this group shared memory, this is visible to all 4 SIMDs. So that's why L0 cache is visible to only to a compute unit, and the group shared memory, so the local data share is visible to the whole dual compute unit, so to all 4 SIMDs. So what does all this like level of caches and local data share mean to you as a programmer? Well, it has an impact in when you want threads to communicate with each other and how long it takes. So let's think about a scenario where you want that all your thread groups communicate with each other. For example, you want to know who is the last active thread group, because the last active thread group needs to do some additional work. And you can figure this out, for example, by using a global atomic counter. So basically what we do is, we have this counter, and as soon as one thread group is finished with its work, it's reading this counter, it's checking its value, and when it does have not reached the number of total thread groups we are running, then it's just increasing the counter. So basically, thread group 0 is finished, it reads the counter, returns 0, so it's not the last thread group, so it's increasing the counter. Then the next thread group finishes, reads the counter, or it's not the last one, it's increasing it. And what's important here is that all the thread groups, they have to see what the other thread groups are doing on this counter. So for example, thread group 1 is reading the counter and then increasing it to 2. But if the value 2 is, for example, stuck in L1, and thread group 9 is running on a complete different dual compute unit, which is not in the same batch of 5 dual compute units, it's not seeing this value 2. So it will read actually the value 1, and then when it's increasing the value, it's 2 again. That's why we have to make sure that the value, the thread groups Y, like the increased counter, is actually flushed to L2, because L2 is the first level of cache that's visible to all threads. And we can do that by marking our counter with the global coherent flag. Globally coherent just means, okay, we are bypassing L0 and L1. We ensure that our value we write to this counter is at least present in L2, so that every thread from the whole dispatch is able to see this counter. So, but of course, that has an impact on performance, because the L2 cache, to access the L2 cache is a bit slower than accessing the L1 and L0 cache. So that's why if you want that all thread groups are communicating with each other, that has a performance cost. If now thread groups want to communicate with each other within a single thread group, we don't need to make sure that the value is flushed to L2, because we know that a single thread group is scheduled to a single dual compute unit. And a single dual compute unit, wow, we can access group shared memory. If you remember the slide before, group shared memory is the special type of memory that sits on the dual compute unit and is visible to all 4 SIMDs on this dual compute unit. So group shared memory is not a cache, so it's explicitly accessible to you as a programmer when you write compute shaders. So you can write to it, you can read from it. The only important thing is, like, if you write to it and you want to read from it, you have to make sure that all threads are finished with writing, so you have to synchronize between your threads within your thread group. That's the only thing you have to be aware of. Another kind of important thing is, if you want to work with group shared memories, is that group shared memory is banked on RDNA 2 and also GCN. So GCN is the previous generation before RDNA. So they are banked as 32 wide, and this just means that you kind of have to be careful in how to access the data on LDS. So one very common example is if you have a float 4 array and you read the value x, you will have 8 bank conflicts. So what's more performant is if you actually have an array of floats, because then you only have 2 bank conflicts when you read the value x. Okay, now let's go even one step further down. So we we only want to communicate within a single wavefront. A single wavefront, we know, is scheduled to a single SIMD. And if we only communicate between threads on a single SIMD, we can make use of wave operations. So they get exposed via shader model 6, and this is just an example, so quad operations. But there exist a bunch of other wave operations. You can look them up on the DirectX website. But this is really fast. And in this example, so it's a quad operation. So basically, if you have quad read across X, so basically, the thread 0 will exchange the value with thread 1, and thread 2 will exchange the value with thread 3. And yet this, if you are able to use wave operations, I highly recommend to do this, because this is a very fast way to communicate between threads, and also to exchange data, and so on. Okay, so now I talked a lot about how threads can communicate with their model, and how is it performant, what performance implication it has. But how do we access data in the first place, right? Because reading data is usually quite slow, and also like writing data and so on. And there are some tricks you should be aware of, and it can have a significant impact on performance. So it's really important that you have contiguous reads and writes, and try to avoid scattered writes and reads. Because if they are contiguous, it's more likely that your data lies within a cache line. One example, when you read data, and for example, you have a thread group 6411, so it's kind of like 1D. So your thread indices are also like very linear. And then if you just use the thread index to fetch the data from a texture, you will fetch them in a really linear way. So the problem with these approaches is that your texture is not laid out like this in your memory, because usually when you have texture accesses, like from pixel shaders, when you read them, usually you like fetch data from a texture that are really close by. And that means it's not linear, it's more like in a quad pattern, so more like this. And this is also how you should try to access your data. So it's better if you like try to access data in like a quad pattern. So instead of having like an access pattern that's very linear, like 64 times 1, it's better to have like a thread group of like 8 by 8. So the total number of threads is the same, but your access layout, like how you access the texture, is different. And this can have a very like difference in performance when you read the data and how it ends up in the cache. So this is one thing you can play around with. Then if you think about writing, so in compute traders you write to URVs. URVs are unordered access views. And it's important that you write contiguous, but not only contiguous writes, but contiguous writes of whole 256 byte blocks, because that can help maximize bandwidth in compute shaders. So the rule of thumb is, if you have an 8 by 8 thread group, try to write also in 8 by 8 blocks of pixels. And try to write to all channels if possible. So for example, if you have an output texture with 4 channels, but you only compute 3 channels of them, you might think, oh, we can just write 3 channels and just ignore the 4th channel because you don't compute anything for it. But actually, it's more efficient if you also write something in the 4th channel. If like the 4th channel contains some like important data, it can be more efficient that you first load the 4th channel and then just write it again. Or if the 4th channel is like unused at the moment, or you will like write to it in a later pass, then just write some dummy data in this path, so to make sure that you actually really write to all channels. Because then you have like this contiguous block of 256 bytes again, and this really helps to maximize bandwidth. Another example. If we think about our previous example before, so we had one scenario where you had an approach that one thread actually writes 4 output values. You can have different like strategies, like which actual values your single thread is writing. So one could be that actually one thread is writing out like a quad. So basically, first with all this 0 was 0, and then you just increase your index by 1. And you see that you actually like your white pattern is not contiguous anymore if you choose this strategy. So what's actually better is if you choose a strategy like this. So you have like so you increase your index by 8 instead of multiplying by 2 and then just increase the index by 1. Because then per single store instruction, so you write to your output, you actually write to a contiguous block of memory. So really try to think like, okay, what memory do I access with a single like load or store instruction? Is it contiguous? Is it a block or is it linear? And try to play around with it and measure the performance. Also try to play around with different thread group sizes and different strategies, because this can really make an impact on how fast your compute data is. Okay, so the second part about like optimization is about how shaders get actually executed on the GPU. And this is nothing compute shader specific, I would say, because all the shaders basically get executed in the same way. But I still cover this section because I think it's very important when you write shaders, and obviously it's also important when you write compute shaders. And it's also, yeah, if you understand this, you are also more able to like write efficient code. So shaders, they get executed on SIMD. SIMD means a single instruction, multiple data. So that means that all threads have to go through the same instructions. Which means if you have an if-else block, and some threads go the if part, and other threads go the else part, we actually need to go to both parts, because we always have to execute the same instructions for all our threads. So, so basically, if you look at the diagram, it's doing something like this. So we have like, so the A block is the preparation for our if-else one, then B is our if part, C is our else part, and then D, everything what's after this. On the left is assembly. And basically what's happening is, so before we have our condition, we kind of have to save the current state. So what's happening? So if we go back, so here in the if condition, so all the threads that are currently active are hitting this if condition. And then we kind of have to store per thread if the result was true or false. And this is what's happening here. So we kind of like save the current state. So just saving, okay, which threads are actually doing all these condition tests. And then we save the result per thread. This is this one. So we know, okay, which threads need to go to the if part, and then which threads need to go to the else part. And at the end, we just restore what we saved in the beginning. So if you look at the execution mask, so in this example, then we hit the if condition, all threads were active. So all threads go through to do this condition test. And then the test turned out, okay, the first two threads, they return true, the third thread returned false, and so on. And all these results get stored in our execution mask. And the execution mask is basically just indicating if our thread is active or inactive. So we store the result in the execution mask. Then we enter block B. So block B gets executed for all the active threads. Then after block B, we invert our execution mask so that all the other threads are now entering block C, so the else part. And then when this is done, we are kind of like restoring the execution mask from previously. So we are now leaving the if-else block and just go on with the rest of our code. So we are storing the execution mask, and since in the beginning all threads were active, at the end all threads are active again. So now what's happening if we do this condition and actually turned out, oh, all threads return false. In this case, we can just skip block B entirely because not a single thread is entering this block. So we can just immediately jump to block C. And this obviously is faster than compared to the case where we have to enter both blocks. And that's why it's super important that you try that all your threads within a wavefront are uniform and go always like have like the same results in your condition tests, because this really can speed up performance. Another example about coherency and all these things for texture accesses. So texture access is interesting because traditionally it was only possible like to have like a uniform texture. So, and most of the time it's still the case. So if you load from a texture, so image source load, it's one texture for all threads, right? So you bind your resource, and then you have your threads accessing this resource with different UV values. And then per thread you get a different result depending which texture got accessed. If you look at the assembly, so you have image load, then your loaded data ends up in some vector register, so it's unique per thread, because I assume most threads will like access different texels. Then you have the UV coordinate, which is also unique per thread. In this example, we have actually 3 UV coordinates because it's actually accessing a texture to the array. So basically a texture to the with different slices. So your first 2 vector registers contain the U and V coordinate, and then the third one is containing the slice index. And then your actual texture, so the address of your texture, is actually stored in scalar registers, right? So basically, where the GPU finds the piece of memory it needs to load from. So this becomes interesting now when we actually have an array of textures. So not a texture array, but really an array of multiple textures. But it's not so interesting if your index is constant, because then obviously all of it are still accessing the same texture. So now we have image source, and then the index is just 0, so on the assembly side nothing changes. But what happens now if our index is not constant, but it's non-uniform? And this wasn't possible for many years, but at some point, you got this feature that you actually could pass a non-uniform index. But you have to mark it, because by default, the compiler will still assume your index is uniform. So you have to specifically mark it and say, no, this index is non-uniform. So this is really important that you mark it. Otherwise, the compiler won't do the, so it's not guaranteed that the compiler will actually generate the correct code. So you mark it's non-uniform, and then potentially each thread could access a different texture within the array. So, but I just told that the address of the texture is stored in scalar registers. And scalar means it's the same for each thread. And this is still true, even though we have this non-uniform resource index flag. The address is still stored in scalar registers. It's just how it works. So what's happening now? Well, what's happening is that now for each unique texture, we have to have a separate call. So we have to have this image load instruction for every single texture. So you have to go through it multiple times if you have multiple textures to access. And this is also called waterfall. So basically, the compiler will iterate for all the threads which have a different texture index and load them one by one. So what's happening? So in the beginning, we still have our execution mask, and the compiler will start with the first active thread. We'll pick the descriptor, the texture of this thread. Then it will check if other threads are accessing the same texture. It's deactivating all other threads. It's loading the values from the specific texture. And then for these threads that are already loaded, the values, we basically mark them as, okay, done, so they can exit the waterfall. And then it will go through to the remaining threads. It will pick again the first active thread, check if there are other threads that are accessing the same texture, loading the values, let them exit the waterfall, and once again, until we've processed all the threads and we have loaded all the values from the unique textures. And you can see this can be quite expensive if you have a lot of textures to access per wavefront. So even though you have now the ability to have non-uniform indices to access your textures within an array, be careful with that, because it can be really expensive. Because texture accesses are slow, and when you access textures from different textures per instruction, then it's also really messed up with the caches, and yeah, so be careful with that. Even though you have now the power to do that, yeah, just be aware of what's actually happening. Okay, so now it's the last part, and it's about export. So basically, export is actually nothing from compute shaders, because the compute shader is not using the shader export. So this guy. The shader export is used by vertex shaders and pixel shaders. So basically, if you have a vertex shader and then the export, it goes to the primitive assembler. And if you have pixel shaders, the shader export will route it to the column backdef end. Compute shaders don't have shader exports because you write your output directly via UIVs. But this also means that a compute shader cannot be export bound. So pixel shaders, they can be blocked from exporting by other ways because exporting actually takes time. Yeah? And while the shader is waiting to be able to export, it still is occupying all the resources. So your pixel shader is done. You just need to export the values. But if your shader export is still busy with exporting the values from other wavefronts, it basically has to wait. And it's still reserving all the resources. And if you don't have enough resources available to launch new wavefronts, that means we're actually blocked by the shader export. And compute shaders do not suffer from this. So basically, if you have a compute shader that's export bound, it can be beneficial to move to compute shaders in this case. So we usually tend to see this when we have highly varying word logs, that it makes sense to move to compute shaders because we are not blocked by this specific hardware unit, or also when we overlap pixel shaders with compute shaders, and the pixel shader is using the export engine, the compute shader is not blocked by this. So this is already the end. So the conclusion. So computer shaders are very flexible. So in my example, I showed how to do full screen passes. This is maybe not even the best example because you can do full screen passes using the graphics pipeline as well. But you can use compute shaders really for anything you want. Yeah, it's basically just you load a piece of data from memory, you do some computations on it, preferably parallel computations because you're doing work on the GPU, and then you just write out some piece of data, and that's it. How this data looks like is really up to you. And in graphics pipeline, you have this structure. So you load geometry, it's processing on vertices. Then you have the rasterizer, it's determining how many pixels get invoked. And then you work on these pixels, and you go and you export it, and that's it. And compute shaders is really, it's really up to you. Then also, compute shaders do not use the fixed function pipeline stages. That means if you have graphic pipelines passed, that makes heavily use of it. So maybe if your graphics pipeline work is making heavy use of the rasterizer, it's a very good candidate to overlap this with a compute shader, because then these both passes basically use different units of your hardware. And a very classic example of this would be to overlap shadow maps with ambient occlusion. Yeah, I think when when you do async compute, if you look up in the internet tutorials or examples, I think that's one of the first examples would say, okay, this is actually a good use case to do async compute. So you have on the graphics pipeline shadow map rendering, and then on the async compute, you have ambient occlusion, because they traditionally use different pieces of your hardware. So you're not, so yeah, it's basically a good use of the hardware simultaneously. Then if you use compute shaders, efficient use of cache is essential. Well, it's not just if you use compute shaders, if you use shaders in general, but I would say in compute shaders you have very explicit control on how you load your data, how you define your threads in what type of work they're doing, how much work they're doing, and how you arrange them, yeah? How you specify your thread group sizes, how they load the data. So that's why you can really play around with compute shaders and see what is actually the best for your specific case. And then, of course, in compute shaders, you have access to group shared memory. You don't have access to group shared memory in pixel shaders. Pixel shaders are using group shared memories, but it's happening under the hood, so it's not available to you. In compute shaders, it is available to you. Then, of course, keep divergence low. Is super important. If you can, try to scalarize your computations to keep, so to make sure that every thread in a single wavefront is accessing the same branch, that you just load from one single resource and not from 32 different ones. And then if you write out to your output target, to your UAVs, make sure you have an efficient write pattern. So for RDNA 2, this means try to write in contiguous 256 byte blocks per wave, because this really can help to maximize bandwidth. And that's the end. Obligatory disclaimer slide. And now it's time for you to ask questions. Thanks.
Hello, thank you for that. I'm wondering, so you don't have to provide the data in a form of a texture, but what about the case where size of your data varies a lot? So should you prepare, I don't know, maybe something like a blank space of certain size so that you feed whole compute shader every time with around the same size? So for example, with neural networks, to train them, you usually have certain fixed size at the start to feed for the computation. But if that data changes quite often, is that applicable for something like this, or?
So I would say it's not that rigid, but there are cache line sizes. So when data gets loaded, doesn't matter if it's from a texture or from a buffer, it always gets loaded in a full cache line. So and to keep that alignment in mind, that can make sense.
Okay, sorry. So I can see that you have AMD here. Do you have any API for AMD graphic cards which are optimized for compute shaders?
So no, compute shaders, I mean, you can use DirectX 12 Vulkan for using compute shaders. You can use OpenCL, but it's not optimized for compute shaders, I would say, because the driver will optimize it for you. So which API you pick, it depends more on your actual use case, I would say. So DirectX 12 Vulkan is when you do graphic stuff, but you can also do graphics with compute stuff. OpenCL is more if you're like really in only compute, but it's not really related to compute shader itself. Because for the hardware, it's just a piece of code you execute.
Yeah, sure, but I was wondering because different graphic cards could utilize different, unique features of graphic cards to optimize the work on them. That was wondering if there is something that you could.
Maybe, but they're not for compute shaders. Like compute shaders are so widely used nowadays. It's like a standard thing. So you don't need any special API for that.
Okay, fair enough.
Hello, thank you for a presentation. Kachmala Mikhailo, CI Games technical artist. It was kind of complex for technical artists. I know that's programmer stuff more, but you have said that it wasn't possible for a long time to mark texture array indexes non-uniform. Does it mean that now we can use like a float value there and it will interpolate between texture slices?
So first, this non-uniform index is not referring to texture slices. Because texture slices is basically if you have like a texture to the array or like a cube map, right? And then you pick the slice. But it's still the same texture. You just have like different views, but the resolution is the same. And in this example, you really have an array of like a bunch of completely different textures, completely unrelated to each other. So like interpolating between two completely unrelated textures doesn't make sense.
Oh, it makes.
Maybe, but yeah, so the index is not float, so you have to access the texture.
Okay, thank you.
Yeah.
Hello, I have a question. What tool you would recommend for profiling the compute shader on AMD hardware? Because NVIDIA have its Insight, which is pretty good, but I cannot find anything for AMD.
We have Radeon GPU Profiler. In general, I would recommend you to go to gpopen.com. There you find all our tools. You also find blog posts, tutorials, also presentations, and you find Radeon GPU Profiler.
Yes, in my case, I'm using OpenGL, and there is not a lot of tool for that. There is a lot for Vulkan, DirectX 12, but not for OpenGL.
I know, and I recommend you to move to Vulkan in that case. But yeah, I know. For OpenGL, we don't have a lot of things, but that's true.
Thank you.
So I just want to ask if, despite maybe not for the hardware limitation, are there any pros over using the computer shaders from AMD over the CUDA? Is there like, do you know if performance is better or something?
So CUDA, I think it's just a language, right?
It's a NVIDIA solution.
Yeah, but so when you write CUDA, I think it's also just a compute shader.
Yes, but it's, if I'm not mistaken, I might be, it's targeted for the NVIDIA cards.
Yes, it is, because it's invented by NVIDIA. Or if you want to do something like that on AMD, you usually use OpenCL, I guess, and then you write your shaders using, I guess, GLSL or HLSL.
Okay, thanks.
Thank you. I have a question because you said that it's better to have 8x8 when you design thread layout instead of 64. But what about the third parameter? So is there any advantage of I don't know, doing something like 4x4 by I don't know 2 or something like this? By 4?
So the reason is why I generally recommend this is just because it's like it represents more like how the memory is actually laid out, like in the hardware. And this is really like block pattern 8x8. And then if you add the third dimension, really you should just you should first load it basically in your like 2D dimension and then move on to the 3D dimension. So if you basically have X, Y, Z, right? Your focus should be first going on like this block pattern and then move on to the third dimension when you load textures. But it depends what you're doing, right? If you just load from like a buffer and you use your third dimension to like mark something else, it could make sense.
Like for example, mesh of vertices, for example, which consists certain data about the world, for example. So they will be by default in 3D. And if they are on certain grid, that could fit the input data quite well.
Yeah, I mean, you can have a 3D grid. And you can use the third dimension, of course. But then I would say, I mean, if you have, for example, 4, 4, 2, then you can walk in the way like you first go along the x-axis and then along the y-axis. And then in the last step, you go along the z-axis, right? Or you can choose you go first along the z-axis and then along the x-axis and y-axis, right? And this can have an impact on performance. Like which axis you go first, if that makes any sense.
Yeah, why?
It's just because the data is stored somehow in memory. And if you first access the first part, like kind of like linear, or first like access this part, and then you go down the z-axis, but this means you access now some data which is stored here, and then when you go back, then you access some data here, you know? So basically you're like, when you look at the data that get fetched and the address, it's more like jumping around compared to when you go first the x-axis and it's actually, okay, now you're accessing this data, then this data, then this data.
Fair enough, thank you.
Okay, I actually see here a question on the monitor. Does it make sense to use second GPU, for example, integrated one, if I also have dedicated one, just for compute shaders, or are there some limitations? I would say it depends. It depends on your use case. One problem is if you use like multiple GPUs is that you somehow have to synchronize between the GPUs, so they have to communicate with each other, right? So if you have like some workload on your dedicated GPU and then you offload some of it to the integrated one, you kind of have to communicate and make sure, okay, when is the work on the integrated one is done, that you communicate it back to the dedicated one. And this overhead can be more expensive than just computing the work completely on the dedicated GPU. So it kind of depends on your specific use case and what type of workload you distribute and how much you have to synchronize between the two. I think that's it.
Hi, thanks. So the basic question, I think, is from a game developer perspective, like what are the traits, like, or what are the messages to that we should use the compute shader? For example, is it like, okay, I have a huge bunch of data that I need to compute? Or is it like, and which gaps we need to like, which are the non-sellers for the solution, for example?
So you're basically asking what type of workload makes sense to use compute shaders, or?
Yeah. For example, like we were, I don't know, like generating a city or something like that, and we have a bunch of data to compute. And originally we make the computing on the CPU, and we are like having an idea, maybe use the compute shader, like for this example, and when we should lean to that solution, and when we like know that it's not the case for this.
Yeah. So compute shaders, I think as long as you have workload that's very parallelizable, since it is executed on the GPU. So you need like workload, that's basically you have a bunch of threads that's doing the same thing, just on different data. Then of course it makes sense to consider compute shaders. And then when you look at graphic stuff, so if you need rasterizer, then I would say just stick to the graphics pipeline, because there is fixed functions. They are in generally faster to do this because they're specifically designed to do this. But if you don't need a rasterizer, for example, then maybe you can think about moving to compute shaders as well. So for example, rasterizer is if you have like a lot of geometry to process, a lot of triangles, so that produces quite a bunch of pixels, then you just use the graphics pipeline. But if you don't have that, like for example, for a full screen pass, you just have one large triangle, you already know which pixels get involved because all of them, then you can just use the compute shader.
Okay, so you've mentioned ambient occlusion and shadow map. Do you have any kind of like most used cases for the compute shader like this, for example?
Yeah, so traditionally what I see for compute shaders is a lot of post-processing effects. So ambient occlusion, also lighting, deferred lighting is often on compute shaders. Any kind of filter, so sharpening, upscaler, compute shaders. They're also seen like terrain transformations on compute shaders, so really a lot of different things. And people get creative, so.
Okay, thanks.
Okay, I think that's it. Thank you all for joining, and you can catch me later after talk. I will be there to answer questions.